Hi, in this video we will learn about an operation between vectors called dot product. So if you give me two vectors with the same number of components, we can find dot product of these two, which is a number. And well, then we will do some examples and study the properties of dot product. Okay, let me just start right away by definition. So I need two vectors, so let u be a vector u1, u2 up to un, and v to be v1, v2 up to vn. Be two vectors, well, they have n components, so they are from the Rn vector space. Okay, then the dot product of u and v. So the way we denote it is denoted by u dot v. That's the naming is clear enough. Is a scalar, so that is a very important point. Dot product of two vectors is a number given by. So when you have u dot v, what you do, you multiply first component to the first component, second to second, and then continue to nth component to nth component. These are numbers, then add all these numbers and get the number which is u dot v. So this is the definition, and this happens for all vectors, so all Rn's, all pair of vectors with the same number of components. So let's do an example. Find u dot v for the given pairs. The first one, u is, well, this is two-dimensional, so 0, 1. And v is 3, 4. And the second pair is u coming from R4, 1, 4, negative 1, 2. And v is negative 3, 1, 5, and then 0. So u dot v, first component to the first component, second component to the second component, add them. So you get 0 plus 4, which is number 4, scalar 4. How about this one, u dot v, first component times the first component, second component, second component, third component to the third, and fourth, then add them. This gives us negative 3 plus 4 minus 5 plus 0. And while this gives us negative 8 plus 4, which is a negative number. Scalar dot product can be a negative number, positive number, 0, any number possible. Okay, this is nice. So we learn how to find dot product. Let me just put a remark here. There are other names for dot product, other names for dot products. Well, people will sometimes call it scalar product, because the result is scalar, and sometimes people call it inner product. But we would use a dot product as the standard notation, as the standard terminology for our course. Okay, so that is done. Then how about the properties? Properties of dot product. Well, first property, oops, I need to change that. The first property is that, well, when you dot u to v, what do we do? So let me write it here. So basically we have u1, u2 up to un dot to v1, v2 up to vn. But the result is this number, u1, v1, u2, v2, and then this goes up to un, vn. See that these are product of two numbers, and remember 3 times 2 is always 2 times 3. The multiplication of numbers is commutative, so we can switch the order. And when you switch the order, this is as if we multiply v, so we have the components of v first, 2 components of u. Remember this property that we can change the order of sum vector addition. Now we can change the order of dot product. And this is what's called commutativity, or dot product is commutative. The second property is that, well, dot product and vector addition work nicely. So it is u dot v plus w is, well, distributes on the sum. So it's u dot v plus u dot w. And everything, so for a proof, the important note for the proof is this, that when you go to the components, so we have ui, the ith component of v plus w is v plus w is vi plus wi, yes? So then what you do is, these are numbers. In the numbers, we have this distributivity, and you will get vi, vi, and then we get ui, wi. So this is basically the key point in the proof of distributivity of vector dot product and vector addition. So this is called distributivity. Or distributive. Okay. So that's the second property. I suggest you try to complete the proof of that part. Also, there is this fact that dot product and scalar multiplication work nicely together. It means that, well, you can first do dot product and then do scalar multiplication, or you can scalar multiply to one of these vectors and then use the other one. Okay, and then there is the last property that I want to mention here is that, well, when you have you can dot product any vector to itself. So what you have is that, okay, I have u1, u2, un dot u1, u2, un. And dot product means that first component first, second, third, up to nth n. So u1 times u1 is u1 squared, u2 squared, and this goes up to un squared. So you have sums of squares of components. And this number, each one of them, you remember that in the real numbers, if you square a number, that would be positive numbers. So all positive. And you have sums of positive numbers, these are going to be positive. So the result says that this is positive. And an interesting thing, when does that become 0? So u dot u is 0 if and only if u is 0 vector. And why is that? Well, first of all, you see that 0 vector dot itself is, well, 0 times 0, 0 times 0, and you add all these things and then you get 0. This means that we have one side. So u is 0 implies that u dot u is equal to 0. But if and only if means that not only the left hand side implies the right hand side, the right hand side also implies the left hand side. So we just showed one side. On the other hand, you see here the u dot u. If u1 squared plus u2 squared plus un squared is equal to 0, so I'm starting from the left, we have sums of positive numbers 0. That means that each one of these guys are going to be 0. So u1, u2 squared is 0, and un squared is 0. Well, if ui squared is 0, then that thing itself is 0. And that is how we prove this thing, that u dot u is equal to 0 if and only if u is 0 vector. So these are 4 properties. We will get back to this u dot u very soon in the other video. But let me finish this video with one more remark about the remark. So in the case of 2 and 3, we can use the commutativity. So 1 can be combined by 2 and 3 to show that, well, here you see for 2, if you 2 says that from the right hand side dot product expands on or distributes on the vector addition. Yes, but this is also true from the left. So if you have v plus w dot u, this will be also v dot u plus w dot u. And why is that so? Because you see w plus v plus w dot u, we can use commutativity and switch the order. Yes, when you have this, now we can use property 2 and distribute dot product over the vector addition. Now each one of these ones, again, we can use commutativity. We can change the order. Yes, and well, what we have proven is what we were looking for. U plus v dot u is v dot u plus w dot u. And similarly, you can show that c dot u, c scalar product of c and uw is not only cu w, but also it is u dot cw. Try to prove this one yourself. You have all the tools you need, and you need to somehow combine 2 and 3 to prove this one. Okay.